Hey guys, I'm Anuj and welcome back to Ink and Metal's Crash Course series. Today we're going to be talking about PID tuning for a motor and FTC, and this will be part one of our two-part series where we're first going to cover what PID is and then go into the practical application with coding it. Let's get started. First, what is PID? PID stands for Proportional Integral Derivative. Essentially, when you're using a motor, you would use PID to arrive at your current, or rather your intended position. And you use your encoder positions for this. Now, what you do with PID is you have a motor, and say it's moved for maybe 2,000 encoder counts, but you want to move it for 5,000. And really, this motor could be applicable in anywhere, like linear slides, for example. Now, you have 2,000 encoder counts done and you want to get to 5,000. And that means you have an error of 3,000. What you want to do, though, is get to 5,000. And for that, you need to apply a certain amount of power. To determine how much power you need to add, you can use PID. Essentially, you take your reference or your current position where your motors are right now, so that would be the 2,000 encoder counts. Then you find your error. That would be 3,000 encoder counts because you just subtract that from 5,000. Then, once you have 3,000 encoder counts, you take into account these three constants which you have to tune and find for yourself: Kp, Ki, and Kd, each representing proportional integral derivative, respectively. Once you take those three constants into account by applying them in mathematic formulas, you would produce your output power. That power is what you're going to set your motor to move on to that final encoder position, 5,000. The reason you want to use PID, however, is so that when you go to your encoder position, you don't either undershoot or overshoot. Rather, you oscillate until you get to exactly 5,000. Because what happens with motors, if you want to get to 5,000, maybe you'll get to like 4,950. Or maybe it just gets like 50 above 5,000. But if you want to make it self-correct and sort of slow down as it gets more and more accurate or closer to 5,000, you'd use PID there. Now, like I said before, PID has three parts, these three constants over here, which must be tuned. And you can see from this graph, it's essentially what we're talking about here. You take your reference, find your error, then you use the value, their constants over here, to generate an output for your motor power. You can actually visualize this on a graph based on your error. Now, there are a lot of applications for PID. Here are just a few that you would use in FTC. So the first one is linear slides. So say you have your linear slides and you want to extend them until you get to some certain distance or encoder count, and you want to stay at that position. When you have your linear slides extending vertically or really adjust against gravity, that's going to be difficult to do with just using the normal way where you just power the motor on until you get to encoder count position. You want it to stay there because gravity would act upon it. Same thing for just generic motors in any mechanism you have, as well as drivetrains. The most popular method of implementing PID for drivetrains is with Roadrunner, which we're actually going to be looking into when coding this up. Here are some best practices for tuning. So like I said, Kp, Ki, and Kd are unique values which you're going to have to find yourself based on experimentation that work for your motor, drivetrain, or whatever. Now, ideally, rather, the best practice is to start with Kp and Ki and Kd equal to 0. These are pretty small constants, however, the values can fluctuate. For example, most of ours are much less than 1, just for context. Now, what you're going to do is keep increasing Kp until the error is low. Now, once that's sort of to your approval, then you're going to increase Ki until you have a steady state error that's removed. And then Kd is increased until oscillations are completely removed. So really you just increase it in the order of Kp, Ki, and Kd. That's the best practice for when you're tuning. Now for the coding, you will have to have a few things set up in your project before we begin. The first is a project from Roadrunner, which you can download from the learnroadrunner.com website. This will give you access to the FTC dashboard as well as other files which you might find useful. Next, you're going to have to install FTC lib for Java for FTC. FTC Lib and Roadrunner are really helpful libraries which I encourage you to look into after this video. That's it for part 1 of this series. Part 2 will be coming out soon with a coding example, and thank you for watching. More videos are on the way, and be sure to subscribe and like our channel. Thank you.